Every time a massive jetliner touches down, it hits the runway at over 170 miles per hour, bearing the weight of hundreds of tons. It's an impact that seems impossible for any rubber tire to withstand, let alone survive. A tire hitting the ground at highway speeds, supporting the weight of a small building. How does it not explode into 1,000 pieces every single landing? The answer is a marvel of multi-layered engineering and material science. At the heart of an airplane tire's resilience lies its incredible inflation pressure. Unlike your car tire, which might be pumped to around 30 to 35 pounds per square inch, an aircraft tire is typically inflated to a staggering 200 to 220 psi, sometimes even higher. This extreme pressure makes the tire incredibly stiff and robust, distributing the enormous weight and impact forces across its entire structure more efficiently. Imagine trying to crush a perfectly inflated basketball versus a slightly deflated one. The former is far more rigid and resistant to deformation. This rigidity is crucial for preventing buckling or blowouts under immense load. But it's not just air inside. Airplane tires are filled with pure nitrogen gas. Why nitrogen? Because it's an inert gas, meaning it doesn't react easily with other substances. This is vital for several reasons. Nitrogen is much less susceptible to thermal expansion and contraction than regular air, providing more stable pressure across the wide temperature swings tires experience, from freezing high altitudes to scorching hot runways. Crucially, nitrogen also lacks oxygen, preventing internal oxidation of the tire's rubber and internal components and eliminating the risk of internal combustion if the tire were to overheat. It's a key safety measure, ensuring stability from the inside out. Yet, even with that extreme pressure, a simple rubber tube wouldn't survive. The true strength comes from the tire's sophisticated construction, a marvel of material science. An airplane tire isn't just one layer of rubber, it's a complex composite, built from multiple plies of synthetic rubber compounds reinforced with strong fabric cords. These cords, often made from high-strength nylon or aramid fibers like Kevlar, are laid in crisscrossing layers, creating a dense, incredibly strong matrix. Think of it like weaving many sheets of a super-tough fabric into a singular flexible belt. This multi-ply structure provides exceptional resistance to cuts, punctures, and the intense G-forces of landing. Each layer works together, distributing stress across the tire's entire surface and preventing a localized impact from causing a catastrophic failure. The outer treads themselves are crafted from specialized synthetic rubber blends designed to withstand extreme abrasion, immense heat generated by friction, and provide maximum grip on wet or dry runways, all while enduring repeated cycles of inflation, deflection, and rebound. The outer treads themselves are crafted from specialized synthetic rubber blends designed to withstand extreme abrasion, immense heat generated by friction, and provide maximum grip on wet or dry runways, all while enduring repeated cycles of inflation, deflection, and rebound. Unlike car tires, which might have 4 to 6 plies, an aircraft tire can have anywhere from 14 to over 30 plies, engineered for an entirely different magnitude of stress. Even with such incredible strength and smart construction, the forces at play can push materials to their limits. What if extreme conditions, like severe braking, generate so much heat that the tire's internal pressure builds to dangerous levels? This is where an ingenious passive safety feature comes in, the fusible plug. Integrated into the wheel assembly, these small metal plugs are designed to melt at a specific predetermined high temperature, usually around 350 to 400 degrees Fahrenheit. If a tire overheats, for example, due to prolonged braking during an aborted takeoff or an unusually harsh landing, the fusible plug acts as a pressure release valve. Instead of the tire exploding violently and uncontrollably, the melting plug allows the nitrogen gas to escape in a controlled manner, preventing a catastrophic blowout. It's a brilliant engineering solution that prioritizes safety, turning a potential disaster into a manageable event. This level of built-in redundancy and fail-safe design is why aircraft tires undergo unbelievably rigorous testing, from simulating high-speed landings on specialized dynamometers to extreme load and impact tests, ensuring they can perform reliably even under the most demanding scenarios. So, the next time you see a massive airliner gracefully kiss the tarmac, you'll understand it's not magic holding those tires together. It's a deliberate, multifaceted engineering triumph. It's the ultra-high-pressure nitrogen providing rigidity and stability, the complex multi-ply construction with advanced materials distributing stress, and the ingenious fusible plugs safeguarding against extreme heat buildup. Each component works in concert, forming a robust system designed not just to withstand the impossible, but to make extreme landings a routine, safe event. This layered approach is why airplane tires are among the most reliable components on one of the world's most complex machines. As aviation technology continues to evolve, what further innovations do you think we might see in tire design to handle even faster, heavier, or more sustainable aircraft?